In 2013, Elon Musk published a white paper titled Hyperloop Alpha. It described a transportation system in which passengers would travel inside pressurized capsules through low-pressure tubes at speeds approaching 1,200 kilometers per hour, roughly the speed of sound at sea level, powered by linear induction motors and using air bearings or magnetic levitation to eliminate friction between the capsule and the tube. The white paper was, by the standards of formal engineering documentation, unusual. It was written in a speculative register, acknowledged numerous engineering challenges, and explicitly invited other engineers to improve on or build upon a concept. Musk disclaimed any intention to develop the technology himself and made the concept open source. The reaction was immediate and bifurcated. Entrepreneurs saw a multi-billion-dollar transportation market disruption and rushed to develop Hyperloop companies. Engineers pointed out that the white paper had significantly underestimated the engineering complexity of several key elements. Both reactions were correct. What the Hyperloop concept represented, and what the serious engineering analysis it generated has clarified, is the application of a set of physics principles that individually are well established to a combined transportation system that is genuinely novel in its integration. The physics works. The engineering challenges are real and substantial. And the underlying concept connects to a longer history of vacuum tube transport proposals and magnetic levitation technology that provides important context for where the technical difficulties actually lie. The speed limit of conventional wheel transportation is set by air resistance. A vehicle moving through the atmosphere at high speed encounters aerodynamic drag that increases with the square of velocity, double the speed, and you quadruple the drag force. At very high speeds, the energy required to overcome drag becomes the dominant constraint. This is why commercial aircraft, which operate at altitudes where the atmosphere is thin, can travel at speeds that would be impossible for ground vehicles in dense sea-level air. The Hyperloop concept addresses this constraint by reducing the air pressure inside the tube to a fraction of atmospheric pressure. The white paper proposed approximately 100 pascals, compared to the sea-level atmospheric pressure of approximately 101,000 pascals. At this near-vacuum pressure, aerodynamic drag is reduced by a factor of roughly 1,000, allowing capsules to travel at very high speeds with manageable propulsion requirements. The remaining drag at low tube pressure comes primarily from two sources: the aerodynamic interaction between the capsule and the tube walls. The capsule must push air through the annular gap between itself and the tube, which becomes significant as the gap becomes small relative to capsule speed, and mechanical friction between the capsule and the tube, if any contact exists. The Kantrowitz limit, an aerodynamic principle described by engineer Arthur Kantrowitz in 1947, sets a fundamental constraint on capsule size relative to tube diameter. If the capsule's cross-sectional area exceeds a certain fraction of the tube's cross-sectional area, the airflow around the capsule becomes choked. It cannot move past the capsule fast enough, and the capsule effectively acts as a piston, compressing air in front of it. This compression creates enormous drag forces and limits achievable speed. Musk's white paper proposed a compressor at the front of the capsule that would actively take in air from the front and exhaust it at the rear, preventing choking and allowing a smaller tube diameter than would otherwise be possible. The elimination of contact friction between capsule and tube is the second major engineering requirement, and it connects directly to the history of magnetic levitation technology. Magnetic levitation, Maglev, uses magnetic forces to suspend a vehicle above a guideway without physical contact. Two primary approaches exist: electromagnetic suspension, which uses conventional electromagnets whose current is actively controlled to maintain levitation, and electrodynamic suspension, which uses the interaction between superconducting magnets on the vehicle and induced currents in the guideway to produce passive levitation. Japan's SC Maglev system, the fastest operational rail technology in the world, with a record speed of 603 kilometers per hour set in 2015, uses electrodynamic suspension with superconducting magnets. Germany's Transrapid system, which operates commercially in Shanghai, uses electromagnetic suspension. Both systems have demonstrated the core technology at commercially relevant scales. The application of Maglev to Hyperloop requires adapting these technologies to operate in a low-pressure tube environment. The magnetic systems themselves are largely unaffected by air pressure, but the support infrastructure, the tube structure, the interface between the capsule and the guideway, the emergency systems, must all be designed for operation in near-vacuum conditions with robust safety provisions. Musk's original white paper proposed air bearings rather than magnetic levitation as the primary suspension mechanism, cushions of pressurized air between the capsule and a smooth tube surface. Subsequent analysis and development by Hyperloop companies has largely shifted toward magnetic levitation as the more technically feasible and scalable option, drawing on the Maglev technology base that already exists. The engineering challenges that have proven most formidable in practical Hyperloop development are not primarily in the physics of the capsule-in-tube system, but in the infrastructure and operational requirements of a working transportation network. Tube construction at the scale of a transportation network, hundreds or thousands of kilometers, presents structural engineering challenges that drive the cost of any Hyperloop system to levels that are difficult to reconcile with conventional transportation economics. The tube must maintain low pressure across its entire length, which requires that the entire length be sealed to a standard that prevents significant air leakage. Any tube section that develops a leak reduces the pressure reduction throughout the network, increasing drag for all capsules. Maintaining a near vacuum in a tube that traverses terrain with temperature variations, seismic activity, and the physical stresses of weather requires either extremely robust construction or continuous monitoring and maintenance. The tube must also be structurally supported along its entire length, which for most proposed routes means either elevated pillars similar to elevated rail infrastructure or underground tunneling. Both are expensive. The per-kilometer cost of building the tube structure has consistently been estimated by independent engineers at figures significantly higher than Musk's original white paper suggested, with more recent project analyses in the range of $20 to $60 million per kilometer depending on terrain and construction method. Emergency systems present a particularly difficult design challenge. A passenger capsule traveling at 1,000 kilometers per hour inside a sealed, low-pressure tube cannot simply stop and have passengers exit if a system failure occurs. Emergency deceleration from this speed, even at the maximum deceleration that passengers can tolerate without injury, requires several kilometers. Emergency pressurization of the tube section where a capsule has stopped must occur before passengers can exit into the tube environment. Emergency evacuation from inside a pressurized tube that may be miles from the nearest exit requires systems that have no close analog in existing transportation. Several Hyperloop development companies emerged after the 2013 white paper. Virgin Hyperloop conducted the first human passenger tests of a Hyperloop system. In 2020, reaching speeds of approximately 160 kilometers per hour on a short test track in Nevada. The company subsequently shifted its focus away from passenger transport toward cargo applications and eventually restructured. Hart Hyperloop, Zaleros, and other European ventures have conducted smaller-scale demonstrations. The regulatory framework for a transportation system that does not fit existing categories. Not a rail system in the conventional sense, not an aircraft, not a road vehicle, has been identified as one of the most significant non-technical barriers to commercial deployment. Regulatory agencies in most jurisdictions lack established frameworks for certifying passenger safety in a vehicle traveling at near-sonic speeds inside a sealed low-pressure tube. Creating these frameworks requires defining safety standards for a system type without operational history, which is inherently conservative and time-consuming. The technology that comes closest to commercial Hyperloop reality is the SC Maglev system operated by JR Central in Japan, which uses superconducting magnetic levitation in an enclosed guideway, though at atmospheric rather than reduced pressure. The proposed extension of the SC Maglev Chua Shinkansen line between Tokyo and Osaka would demonstrate sustained maglev operation at over 500 kilometers per hour across several hundred kilometers of tunnel and elevated guideway. the longest and most demanding operational test of the relevant technologies at near Hyperloop scale. The promise of the Hyperloop and its Maglev relatives is straightforward. Transportation at speeds that reduce the effective distance between cities to the point where they become, for practical purposes, part of a single metropolitan area. Los Angeles to San Francisco in 35 minutes. New York to Washington in under 15 minutes. Paris to Berlin in under an hour. At these travel times, the geography of economic concentration shifts. Talent markets expand. The premium on living in any specific city declines relative to the premium on being in the network. The physics permits this. The engineering challenges are real, but not fundamentally intractable. They are challenges of cost, regulatory framework, and operational complexity, not of unknown science. The question is whether the economics work at a tube construction cost that any government or private consortium would actually pay. The answer to that question is still being worked out. The capsules are ready in concept. The tube is the obstacle.